Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at Diophantine equations. They are so named because the person who came up with them, I think, was named Diophantinus. So Diophantine equations look like this. They're of the form ax plus by equals c. Here a, b, and c are constants. They're numbers given to us, and we want to solve for x and y, but moreover, we want x and y to be integers. So an example of a Diophantine equation is 5x plus 8y equals 7. So to solve that, we want to find integers x and y that make this statement true. So in this equation, we have a is 5, b is 8, and c is 7. But these equations won't always have a solution. So Bazauer's identity tells us when there is a solution. There will be a solution to ax plus by equals c. There will be an integer solution for x and y if and only if c is a multiple of the highest common factor of a and b. It turns out if there is one solution, there will be infinitely many solutions. But it's really important that we have that c is a multiple of the highest common factor of a and b. Otherwise, we would get weird equations like this. So 12x plus 8y equals 7 has no integer solutions. So why is that? Well, just think of it like this. 12 times an integer, that would be even. 12x would be even for any integer x. 8y would be even for any integer y. It's impossible that we can add together two even integers and get an odd integer. So in terms of Bazauer's identity, the thing here is that the highest common factor of 12 and 8 is equal to 4. 7 is not a multiple of 4. That's why this equation here would have no solution. However, 5x plus 8y equals 7 would have a solution because the highest common factor of 5 and 8 is 1. So 7 is clearly a multiple of 1. So this will have a solution. So how do we actually find such a solution? How do we find more than one solution? Well, it turns out we use the extended Euclidean algorithm, which I'll go through now. So let's look at solving this here using the extended Euclidean algorithm. So the idea is we're going to start by calculating the highest common factor of 5 and 8. Now, I know that you know that's 1. That's really obvious. But we still want to write the Euclidean algorithm because it gives us the steps. We're going to actually reverse it to find the solution here for x and y. So, Euclidean algorithm. We start with the larger number and basically subtract multiples of the smaller number. So 8 is 1 times 5, and then there's 3 left over. And then the highest common factor of 5 and 8 is the same as the highest common factor of 5 and 3. So let's repeat the process. So 5 is equal to 1 times 3 plus 2. Then we write 3 by subtracting multiples of 2 with a remainder. And then we end up with 2 equals 2 times 1. So we've ended up with 1 down the bottom. So the highest common factor of 5 and 8 is 1. Yes, that's really obvious. But this is going to help us come up with the values of x and y. So what we're told here is we start with our highest common factor, which is 1. So this line tells us to write 1 as 3 minus 2, subtracting 2 from both sides. This next line tells us to write 2 as 5 minus 3. So I'm going to replace this. It's going to be 3 minus 5 minus 3. Which ends up being 2 times 3 minus 5. So the next line tells us we're going to replace the 3 here with 8 minus 5. So we get 1 is 2 times 3, which is 8 minus 5. So that's 2 times 3 minus 5. So just simplifying that, I get 2 times 8 minus 3 times 5. So we've actually used the extended Euclidean algorithm to solve the equation 5x plus 8y equals 1. So how do we make 5x plus 8y equals 7? All I need to do is multiply everything by 7. I multiply 1 by 7. So multiplying this by 7, 2 times 8 multiplied by 7 just gives me 14 times 8. And then I multiply 3 times 5 by 7. So I have solved the equation here. 7 is equal to 14 times 8 minus 21 times 5. So a solution to this equation, y equals 14, x equals negative 21. So even though we knew the highest common factor of 5 and 8 really simply, we still need to write out the Euclidean algorithm so we can reverse it and get our solutions to the Diophantine equation. So this is one such solution. How can I find more solutions? Well, we're just going to use the lowest common multiple. See, the lowest common multiple of 5 and 8 is 5 times 8 divided by highest common factor. 5 times 8 divided by 1 is 40. How am I going to use that to come up with other solutions? Well, I could just keep subtracting multiples of 40 from this part of the equation and adding multiples of 40 to that part of the equation. So, for example, I have my solution 7 equals 14 times 8 minus 21 times 5. What I could do to come up with another solution is I could add 40. I could add 5 more lots of 8 as long as I take away 8 more lots of 5. So on. So in general form, what I have as a solution, I've got y equals 14, and I can just add integer multiples of 5. So here k has to be an integer. And for x, I had my original solution was negative 21, and I just need to subtract integer multiples of 8. All of those will be solutions because 14, negative 21 for y and x respectively, that was a solution. If I keep adding multiples here, an integer multiple of 5, this will be adding multiples of 40 and this will be taking away the multiples of 40, so I'll still end up with my answer 7. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.